There we go. Okay, so for 2.6, we are talking about rational functions and their asymptotes. So a rational function is a function with a variable in a denominator. It can be as simple as something like 1 over x to something much more complicated like x plus 5 over 2x squared minus 3x plus 2. A vertical asymptote is a line that that a graph approaches but never crosses. A horizontal asymptote is a horizontal line that a graph approaches but never crosses. And we're going to look at that on Desmos. So we'll zoom out on these graphs and see that they actually never cross the asymptote. It will just get infinitely close to it, but never actually cross it. So here, the domain of a rational function includes all real numbers except where the denominator is equal to 0. So if I ask you for the domain of a rational function, you're going to set the denominator equal to 0. Then you're going to say, oh, the domain is all numbers except when x equals and whatever you got when you set the denominator equal to 0. So find the domain, set the denominator equal to 0, and solve. The solution or solutions are where the function is undefined. So I put that solution / solutions there because sometimes we may have a quadratic. It has values that you can solve for x when you set it equal to 0. Or maybe there are 3 zeros or 3 asymptotes when you set equal to 0. It is possible, hence why I put it as a potential plural. Okay, find the domain of this function. So what I have to do here is I need to set the denominator, x squared minus 9, equal to 0. Now I notice since it has an x squared, this is a quadratic. We could technically do the snowflake with it if we wanted, with -9, 1, 1. And since there's no actual b term, there's no x in the middle, that would be 0. So I realize this factors to a +3 and a -3. Again, I know I've had you guys practicing factoring for a while with your do nows. So if you're like, I don't need to use a snowflake, Isaacoff, I think I figured out factoring well enough, that's fine. You could just jump to this being x plus 3, x minus 3 equals 0. So now we can split this. And when I split this solves x plus 3 equals 0, x minus 3 equals 0. Subtract x equals -3. And x equals +3. So my domain is all real numbers except x equals -3 and +3. So my domain will be all real numbers except when the denominator is equal to 0. So we'll take a look at this graph in a moment using Desmos, and we will see that -3 and +3, if I set x equal to that, we'll see gaps in the graph. So I do want to give you, there's a person, moment to make sure you got that down while I fix this student's attendance, and then we'll look at a visual of this. And fix that student's attendance as well. So this, I'm going to let you know, trying to find the domain is how we also find vertical asymptotes and holes. So setting that denominator equal to 0 is big idea here. We have an asymptote when it does not cancel out with anything in the numerator. But if we see something cancels out in both the numerator and denominator, what's going to happen is it ends up being a hole as opposed to an asymptote. So I'm going to share my screen so we can look at this on Desmos. So the function we got, there we go, Desmos is opening up, was 1 over x squared minus 9. And we notice we have these gaps happening here. So like I said, x equals +3. That was one of them. And when I graph asymptotes, I always like to use a dashed line for them. And we said x equals -3 is the other one. So we actually see those, and those are our asymptotes. Those are those dashed vertical lines that we have gaps in this graph happening there. Again, as I scroll up, we notice this does not want to look like it crosses the dashed blue lines. However, it just kind of sticks with them. And if I scroll down on the other direction, again, we see it just does not want to cross those blue dashed lines. It just kind of sticks to them. That's the idea of an asymptote. So let's get back into the notes, share the note file. There that is. Yes, I know that's not broadcasting. And there are notes. Okay. So here with this notation, if I say f of x and then put the arrow 5, that says f of x approaches 5 as x approaches infinity. So that notation, I just want you to get used to. When you see that arrow tells you approaches. So x approaches infinity, f of x approaches 5. You are going to see that notation a lot more when you get into calculus, but we're starting to bring up that notation now. If that notation's a little confusing now, don't stress it too much. We're not stressing it greatly in this class. We're just exposing you to it. Okay, so let f be a rational function given by the following, where n of d is the numerator, n of x is the numerator and d of x is the denominator, with no common factors. That no common factors is important here. So if there are no common factors, the graph will have vertical asymptotes where the denominator is equal to 0. So again, our big idea here, we're going to want to do with like all these problems, take your denominator and set that equal to 0 to find your vertical asymptotes. So setting the denominator equal to 0, that's our big idea. Okay. Now, horizontal asymptotes. The graph of f has at most one horizontal asymptote determined by the power of the numerator and the denominator. If the numerator has a smaller power than the denominator, that's simply put, it has a horizontal asymptote at y equals 0. And I'll give a common example of this. I know I said this yesterday. Look, if I have 1 over x, has a higher power than just the constant of 1. So that means it has a horizontal asymptote at y equals 0. If I think about this, if I put in some huge number into that, if I said x is equal to 29 billion, 1 over 29 billion is a very small number. It's barely above 0. Above 0. Hence why it approaches y equals 0. You know, if I put 1 over a trillion, that's even closer to 0, but still doesn't get all the way there. Okay. If the powers are equal, we will write the leading coefficients of the function the following. It's just going to be our horizontal asymptote is a over b, where a and b are the leading coefficients that we talked about before. So if they're both x squareds, again, I talked about that yesterday. Like if I have a 2x squared over 3x squared, well, the 2 over 3 is what it would end up reducing to. So it's just going to end up being 2/3. And if the numerator has a greater power, we get what we call slant asymptote. And I think I have one example with the slant. No, I don't have an example with slant asymptotes. We're not going to see slant asymptotes until after spring break when we're graphing that. Slant asymptotes get a little more interesting. I know you guys did well with the polynomial division. I know it wasn't our biggest thing. You know, some of them will have nice denominators we can use synthetic division with, but we're going to have to go back to dividing polynomials to find slant asymptotes. So we are going to find the asymptotes of these functions. I'm going to do both examples all by hand. Then we'll look at the graphs together. Okay, so here with this, I am going to use HA for horizontal asymptotes and VA for asymptotes. So let's start with my vertical asymptotes here. So I want to set the denominator equal to 0. So I am going to factor this. This factors to x minus 3 times x plus 2 equals 0. So this splits off when I solve it. X minus 3 equals 0. X plus 2 equals 0. Add 3. X equals 3. Subtract 2. X equals 2. Or sorry, negative 2. These are my vertical asymptotes. Now I need to determine my horizontal asymptote. For my horizontal asymptote, I notice that I have an x and an x squared. My denominator has the higher power. So if we refer back to the previous slide, when the denominator has the higher power, so the numerator is smaller than the denominator, it's just y equals 0. Y equals 0. So again, keep that in mind. We're going to find it all on this. Then we're actually going to look at both of these together on Desmos and confirm those asymptotes visually. So here, again, same thing happens for my vertical asymptotes. I'm just going to look at this as x squared minus 1 equals 0. Oh, this factors x plus 1, x minus 1 equals 0. Split them. X plus 1 equals 0. X minus 1 equals 0. X equals negative 1. And x equals positive 1 in this case. So those are my vertical asymptotes. My horizontal in this case happens the following. I have basically 2x squared over, I want to say that's y equals, sorry, y equals, I can look at this as like x squared over, or sorry, 2x squared over x squared. I'm just ignoring like the minus 1 now for the horizontal. I go, oh, the x squareds would cancel, just leave me with y equals 2. So that's how we find our asymptotes mathematically. I'm showing you how to find them mathematically because Desmos is great. And if you know how to find them mathematically, Desmos can be an incredibly powerful tool to help you see what's happening. However, trying to find our asymptotes using Desmos doesn't tell us them. We can look visually to approximate where they appear to be, and you can try a guess and check way with Desmos that way. But, I find it rather easy to just do the math behind it and then confirm visually if we're unsure of ourselves. So that is the work for those. I'm going to give you a second to digest that. And if you do have questions, you can put them in the chat before we look at it visually on Desmos. I think I do have another student or two that did come in. Let me double check their attendance. Yes, has been fixed. Good. Okay. Whoop. Sorry, got something in the chat. Yes, so the x squareds are essentially canceling out when we're looking at the horizontal asymptote. Just when we're looking at the horizontal asymptote. We're going to talk about what it means if in the original function form something cancels out. but the x squareds would not cancel out how it's initially written due to the -1 in the denominator. But we will see at least one example where something in the numerator and denominator cancel out, and that's what creates what we call a whole. So great question there. Okay. Let's, whoop. Okay. Sorry, it just looked like something froze on me. Just wanted to make sure I'm still here. So let's share the screen and look at Desmos again with these two problems. Okay. So the first one had said, oh, let me pull those notes back up for myself on my phone. So I already just quickly forgot what the numerator of the first one was. There we go. 2x minus 1 over x squared, minus 1 over x squared minus x minus 6. Okay, as you can see, my asymptotes appear to be off. If we recall correctly, I said one was +3. Oh, wait, that one's right. The other was -2. So let's change this to a -2. Okay, that's lining up. Then I said my horizontal was y equals 0. And again, this purple line appears to work with that. So that's again what we mean with our asymptotes. Again, as I zoom out, I see it might do this kind of weird and strange or funky behavior in other areas, but for the most part, it just wants to be along the asymptotes. Okay, now my next function had said 2x squared over x squared minus 1. So yeah, all my asymptotes look off right now based off the old problem. I had said it was a +1. Okay, that looks like it lines up. A -1. And then I had said, oh, we had done that as 2x squared over x squared, and the x squareds canceled. So that just left us with 2. And now that looks like what I want to see. That asymptote that's horizontal now moved up to where that is. And again, as I zoom out, nothing appears to be crossing those asymptotes. Zoom back in, and we see it there. Again, we're not worried about graphing them just yet, but I want you to see how they're graphed, so it's not a totally brand new or foreign idea when we come back from spring break. Okay, let's get these notes up again. Come on. Okay. When factors cancel, that's when we have wholes. So this is our last example here. So if something cancels out, what happens is it creates a whole instead of an asymptote. So what I want to do here is I'm actually going to factor this before I set the denominator equal to 0. So I can factor this to become, let's see, my numerator would factor to x plus 2 times x minus 1. All over, we know this factors to x minus 3 times x plus 2. Now notice, an x plus 2 in both the numerator and the denominator would cancel. So since they cancel, since x plus 2's cancel, x plus 2 equals 0 is a whole asymptote. So I'm going to get a hole there when I set x plus 2 equal to 0, subtract 2, get x equals negative 2. That's a hole. Now I want to do vertical asymptote. It's going to be what's left in the denominator. X minus 3 equals 0. Add 3 to both sides. X equals 3. So negative 2 is a whole where positive 3 is an asymptote. And then finally, I'm going to look at my horizontal asymptote. Just going to look at the leading part of this. So that's like y equals x squared over x squared. This would just cancel to 1. So that is y equals 1. So here with this is a special function because we get things to cancel out. If we were to look at the graph of x minus 1 over x minus 3, it will look identical on Desmos to the graph of x squared plus x minus 2 over x squared minus x minus 6, because it reduces to that. Just like 1/2 and 2/4 are the same thing, since this reduced that way, these are the same thing. So I'm going to give you a moment to get that down or ask any questions on that before we look at the graph of it. Okay, perfect. We have just about 7 minutes left in class, so that's plenty of time for me to show the graph and the problems for homework. All you're doing is like identifying all this key information. Let me bring those notes back up. Okay. So let's share again my screen so we can look at that on Desmos. So this one said x squared plus x minus 2 over x squared minus x minus 6. Okay, now our asymptotes are way off, as we can already see. Those lines are crossing those ones all willy-nilly. So we had gotten that at x equals 2, x equals 3 is an asymptote. X equals negative 2 was not an asymptote. That was a hole. So actually, I just want to get rid of that. I said this one was y equals 1. Okay, now those asymptotes are looking pretty good to me. As I zoom out, yeah, that's looking really good. If I type in, like I said, this is actually the same as when it reduced, that was x minus 1 over x minus 3. That black graph and that red graph are exactly the same. Well, almost exactly the same. I'm going to show you where our issue is. If I try and drag this point, I said we had a hole at -2. Well, there, come on. There it is. It's very hard to see the hole. Desmos doesn't actually graph the hole, but if you go to -2, you will see it's undefined. If I call this function f of x equals this, and I said f of 0, or not f of 0, sorry, f of -2, we get that's undefined. Whereas on the black graph, if I call that g of x, if I did g of -2, we actually get that one's defined. So on the black graph, when I scroll and get to -2, come on, -2, we get this value, whereas on the red graph, that was undefined. Come on. So again, even though it reduced to that graph, we see that technically, because our original function would give us a 0 in the denominator when we plug in -2, that it ends up being undefined there. When you get into calculus, we'll talk about how to learn, oh, that approaches the value of of 0.6, and you can talk about how you can calculate that in calculus. But I'll save that for then. So stop.